are still in chapter 18, magnetic field created by an electric current. In this part, we are going to make a generalization and to understand the analogy between the magnets and the coil. Now we will start with generalization. At a point of the magnetic field created by a current, the direction of this magnetic field depends on that of the current, and also the magnitude of this magnetic field is proportional to the value of the current. We can say that the magnetic field B equal K multiplied by the current I, where K is a constant depends on the geometry of the circuit and the nature of the medium. What do you mean by the geometry of the circuit? The geometry of this circuit may be a rectilinear wire, a circular loop, a flat coil, or a solenoid. As we said before, B equal K multiplied by the current I. In the first case of a long rectilinear wire, the magnetic field created at a point separated a distance d from this wire is equal to mu0 I over 2 pi d. In the second case, in the case of a flat coil that has a radius r and containing n loops, this is the radius r and this is the number of loops, the magnetic field created at the center of the flat coil is equal to mu0 and I over 2i. Finally, in the case of a solenoid that has a length L and have n loops, this is the length L and this is the number of loops, the magnetic field created inside the solenoid is equal to mu0 and I over L. As you notice in these three different formulas, the magnetic field B is proportional to the value of the current I. Now we will start with the analogy between magnets and coils. A coil, either flat or long, acts as a bar magnet when traversed by a current. By analogy, we assign to each coil two faces, either north or south. We've previously explained it briefly, but now we will explain it in details. This is the coil. By applying the right-hand rule, the direction of the magnetic field is to the right. So, this face of the coil acts as a north pole and that acts as a south pole. So, we can say that the magnetic fields enter to the south pole and leave the north pole. Therefore, we can deduce that this coil acts as a bar magnet. As we said before in the previous videos, this bar magnet creates a magnetic field in the space around it. These magnetic field lines are directed from the North Pole to the South Pole, so they enter the South Pole and leave the North Pole. To understand this idea, let's watch this video. The solenoid carrying current behaves as a bar magnet. The created magnetic field outside the magnet is directed from the North Pole to the South Pole, so they enter the South Pole and leaves the North Pole. Moreover, as you remember, we said that along the magnetic field lines traverse from the South Pole to the North Pole. Look again to the video. Remark, since the coil acts as a magnet, so there is interaction between coils. The like faces repel each other and unlike faces attract each other. In order to distinguish the two faces of the coil, we have three different methods. First of all, by comparing the sense of the current and that of the arrows added to the extremities of letters S and N. We've explained it before in part 3, but to understand it well, let's watch this video. If the current flows in the coil in a clockwise direction facing the observer, then that face of the coil will act as South Pole. If the current flows in the coil in anti-clockwise direction facing the observer, then that face of the coil will act as North Pole. Second method, we can distinguish the two faces of the coil using the right-hand rule. We've explained it before, but we will remember it now. Curl your fingers of your right hand in the direction of the current, then your thumb indicates the direction of the magnetic field. In this case, the magnetic field is directed upward since the magnetic field leaves the North Pole. Therefore, this face of the coil acts as a North Pole, and that of the coil acts as a South Pole since the magnetic field enters it. Third method, we can distinguish the two faces of the coil using the right hand screw action. Simple way to determine the direction of the magnetic field around the conductor is to consider screwing an ordinary wood screw into a sheet of a paper. This is a wood screw. As the screw enters the paper, the rotational action is clockwise. Likewise, the action of removing the screw is the reverse anti-clockwise. Look to the following figure. This is the head of wood screw, so this face acts as South Pole, and this is the wood screw points, so this face acts as a North Pole. Application. The following circles represent the faces of a coil or a solenoid. Determine the nature of each face. Solution. We will solve this application according to the three methods. First method, using the arrows added to the extremities of the letters S and N. Look to the following figure. In the first case, the current flows in the coil in anti-clockwise direction. Then this face of the coil will act as a North Pole. Whereas in the second case, the current flows in the coil in clockwise direction, then this face of the coil will act as South Pole. Second method, using the right hand rule. In the first case, curl your fingers in the direction of the current. Then your thumb will direct it in the direction of the magnetic field. In this case, the magnetic field is outwards the face, so it leaves the face. Then this face acts as North Pole. Whereas in the second case, if you curl your fingers of your right hand in the direction of the current, then your thumb is directed in the direction of the magnetic field. In this case, the magnetic field is inwards the face, so it enters this face. Therefore, this face acts as a South Pole. Third method, using the right hand screw action. The first case is the action of removing the screw. Then, this is the wood screw point. So, the magnetic field outwards the face. Therefore, this face acts as a north face. Whereas, in the second case, the screw enters the paper, so this is the wood screw head. Then B inwards the face, therefore this face acts as a South Pole. This is the end of the lesson. In the last part, we make a generalization, and after we explain the analogy between the magnets and the coil. I hope that you understood the whole objectives that are explained. Everything mentioned in the previous videos is written in the summary sheet to be studied. Thank you for your attention. Good luck.